Okay, so this video is going to go through dilations and reflections. So just a quick review. The translation just moves things left, right, up or down, and we have some special terminology about moving things to the right. We would say moving in the positive direction of the x-axis, or moving things up would be in the positive direction of the y-axis. So we need to know that terminology. Dilations are another type of transformation. What they do is they make things fat or skinny. Okay, so in this example here, right, the blue one is y equals 3x squared. And the red one is y equals x squared. And you'll see having that little 3 there makes the parabola more skinny in this case. And our objective is to understand why this xy goes to x 3y for a dilation by a factor of 3 from the x-axis. So what I'm going to do is pick a point. So along the red parabola, right, that point there is 1, 1. Okay. Now, if I'm looking at the y equals 3x squared, at x is 1, y is 3. There's a 3 there. Okay, so 1, 3. Now let's look at another point. That point there is 2, 4 along y equals x squared. And what is it along y equals 3x squared? Go up. That is 2, 12. So what's happened to those points is that one's gone to that one by a factor of 3. We've gone 1 times 3 to get there. And then that one goes to that one. And that 4 has been multiplied by 3 to give 12. Okay, and the terminology is dilation by a factor of 3 from the x-axis. It's going away from the x-axis. Okay, so dilation by a factor of 3 from the x-axis. Now, another way of writing that is dilation of factor 3 parallel to the y-axis. So why is it parallel to the y-axis? Well, there's the y-axis. There's my transformation that's parallel to it. Okay, parallel, again, parallel. So two different ways of saying the same thing. Alright, and then we have this even more compact way of saying it, is that each xy coordinate gets mapped to the x coordinate stays the same, and the y thing has been multiplied by 3. Alright, so we need to know dilations, and we need to know all of that. The language from the x-axis and parallel to the y-axis, and we also need to know how to write it with this sort of rule. Okay, xy is transformed to or mapped to x comma 3 times y. The next one will go through dilation by a factor of 2 from the y-axis. So in this case, the red one is y equals x squared, and this one is y equals x on 2 squared. Alright, and I'm going to see here, this is the point 1, 1. And it's going away from the y-axis. So it's dilation by a factor of something from the y-axis. Okay, so that one gets mapped to x is 2, y is 1. Alright, let's pick another point. 2, 4, where does that get mapped to? It gets mapped to 4, 4. So what's happening to the x values? They are changing. Right? 1 times 2 gives you 2, and 2 times 2 gives you 4. So everything's being stretched out away from the y-axis by a factor of 2. And we can write it like that, or dilation of factor 2 parallel to the, what do you think? It's parallel to the x-axis, isn't it? Alright, so parallel to the x-axis. Alright, reflections, they're pretty straightforward. You just treat things as mirrors, okay? So here's my y-axis. If I'm reflecting in the y-axis, I want to have a mirror image, so it would look something like that. Okay? So what's happening to the xy coordinates if you're reflecting in the y? Has the x changed or has the y changed? The x has changed. Okay? So it's like a mirror, and we're saying that that distance is the same distance as that distance. A reflection in the x would be the blue one here, and look something like that. And what's happening is that coordinate there gets flipped around, and now the x has stayed constant, but the y has flipped. So a reflection in the x-axis is the x stays constant, but you flip the y. Okay, so that's just a quick little visual video about dilations and reflections.